Hi, my name is Berkay and here I am with another video. In this video, I will going to show you the differences between bandpass filter and a Morlet Wavelet. So I have a data in here, and as you can see, it has two components. One is signal and other one is signal's sampling rate. So let's plot this. And as you can see, this is just a noisy signal. So what I'm going to do is first I will going to create an FIR bandpass filter, and its cutoff frequencies will be between 10 to 15, and I am going to filter out this noisy signal. And after that I am going to create a Morlet wavelet to filter out this noisy signal, and we will going to compare them with each other. And before the start, I must tell you this. This video will be a little bit longer, but I will create a summary video for this content. If you don't have enough time, you can watch that video. Now, let's start. First, I need to specify my bandpass filters cutoff frequencies. So let's start by that. And it will be between 10 to 15 hertz. Now this is the cut of frequencies, and now I can specify my order. So my order will be 20 times round S rate divided by cutoff low frequency. Okay, this is the order. And now I have my cutoff frequencies and my order. Now I can just create my filter. So canner bandpass is equal to, I will going to use FIR function. First I need to specify order of my signal, then cutoff frequencies, and I need to divide them by the Nyquist frequency, which is equal to S rate half of the S rate, which is equal to half of the S rate, and the filter type. And my filter type will be a bandpass filter. This is our filter. Bandpass filter. Okay, now technically I can filter out my signal right here, right now, but I need to check my filter first. I need to be sure that it is working correctly or not. So what I'm going to do is I will going to first check the time domain response of my filter and the frequency domain response of my filter. So let's start by that. I will going to create a figure, and I will going to divide that figure by 2, and let's plot our filter canner, and this is the time domain response of my filter pass filter. Now I need to find frequency domain response of my filter, and to do that I need to create a new time vector. So I'm going to use line space function to create that. It will going to start from 0, and it will going to add at the Nyquist frequency. So what I'm going to do is I will going to use floor function, then length function, and it will be the length of my filter canner, then I will going to divide that to 2 and I will going to add 1. Okay, and this is it. There is no problem in here. This is it. Now what I'm going to do is I will going to plot my signal. First I'm going to specify my new time vector, and oh, I almost forgot. First I need to calculate the power spectrum of my canner. So canner power is equal to absolute Fourier transform of my bandpass fitted canner, and I'm going to square it. I am taking the Fourier transform of first Fourier transform of my canner, and after that I am going to take its absolute, and then I am taking the square of it. Now I can plot it. We're going to start from 1 to length for power vector. Its color will be black, and its line width will be 3. Now let's see. Okay, this is the time domain response of my filter, and just let edit. Let's add a title. Domain response, and this is the frequency domain response of my filter. Okay, now let's do it again. Okay, now this is the time domain response of my signal. You can see it, and this is the frequency domain response. So I need to zoom in a little bit, and as you can see, its cutoff low frequency is 10 and cutoff high frequency is 15, and this is its attenuation period, and I didn't like it. I am going to increase the order of my filter to correct this. This is not a good filter. So what I'm going to do is I will make this 4 to 5, because why not? So let's do it again, and as you can see, this is the time domain response of my filter canal, and it's looking good, and I'm hoping that my frequency domain response will look good, and it's better. It's really better, and now I can filter out my noisy signal, because I know that my filter is working correctly. Now what I'm going to do is I will going to create an fit signal filtered, and I will going to use fit function. First I need to specify the canner one, and then the signal itself. Okay, now let's do it, and MATLAB gave an error, and it's saying that my signal should be longer than 27,675. So this is happening because my filter canner is my filter canner's order is longer than the sampling frequency. So what I'm going to do is I will not going to decrease my order. I will going to create a reflected signal. And let me show you this. So I'm going to create a reflected signal. And what I'm going to do is I will going to take my signal and I will going to reflect it. It will going to start from end and go backwards to start of the signal. Then I will going to add my normal signal and I will going to add a reflected signal again. To 1. Okay, now let's do this and let's see if it's okay or not. So let's do it again. And MATLAB gave another uh, error because as you can see in here, yes, I have tripled the size of my signal, but it is not enough because now it has 3 channels. So what I'm going to do is I will going to add these two and let's do it again. And now you can see that my signal is really tripled right now, and MATLAB didn't give any error. So, but now I need to cut this signal because it is 3 times longer than my original signal. So what I'm going to do is first I need to learn the length of my signal, original signal. No, okay. And now I will going to cut my signal and it will be like this. It will start from n plus 1 and end in the end minus n. Okay, let's create a figure and let's plot it. And title will be Bandpass Filtered Signal. Okay, let's do it again. And this is it. This is the bandpass filtered signal. And now I will going to create a Morlet Wavelet. And now let's create a Morlet Wavelet. We are going to use convolution theorem to filter out these noisy signals, and we are going to use Morlet Wavelet, and we are going to use its frequency domain response because it is much more faster. So let's create our Morlet Wavelet, but first we need to specify some parameters, and first one is peak frequency. So peak frequency will be this, and it will going to equal to 12.5 hertz. Okay, this is okay. This is the peak frequency. Now I need a full width at half maximum value for my Gaussian signal because I need a Gaussian to create a Morlet wavelet. So full width at half maxima is going to equal to 0.25. Okay, now I need a time vector and wave time will be equal to, we start from -3 and 1 divided by s rate and we're going to end at 3. Now I can create my Morlet Wavelet. So Morlet Wavelet is equal to a cosine function 2 multiplied by pi multiplied by peak frequency and time function. And I'm going to multiply it with a Gaussian. So let's multiply it, and this is the Gaussian minus 4 multiplied by logarithm 2 and multiplied by square of our time vector, and it is going to be divided by full width square of the full width at half maxima value. Okay, is everything is okay? This is my cosine function, and this is the my Gaussian, and 4 multiplied by logarithm 2 and wave time squared and divided by 2. Okay, this looks good. Now I need to create a new time vector for the frequency domain response of my Morlet Wavelet. So it will be equal to this. Again, I will going to use line space, and it will going to start from 0 and end in the Nyquist frequency by 2. Okay, now set floor. I am basically doing the same thing. So we are going to use wave time and 2 and plus 1, and this is it. Now I found the frequency domain time vector. Now I need to find the frequency domain of my wavelet. So power, Morlet Wavelet power is equal to 2 multiplied by absolute value, and I'm going to take for the transform of it. Morlet Wavelet. Okay, now this is it, and this is the frequency response of my Morlet Wavelet. So what I'm going to do is I can again, yeah, I can convert my signal, but I'm not going to do that. I will going to check my wavelet first. So let's create another figure, and I'm going to divide that figure to 2, and let's plot our wave time Morlet, and its color will be a black one. It's not okay, and this will let an title, and this will be time domain response of Morlet Wavelet. Okay, now let's plot the frequency domain response of our wavelet. So let's plot Yes, and it will be it from start to length of hmm? Okay, this is it, and it will going to be black again. And let's add a title to it. Frequency domain response of Morlet Wavelet. Okay, fingers are crossed, and let's see. Okay, now this is the time domain response of our Morlet Wavelet, and I need to zoom in to see this one. And frequency domain response of Morlet Wavelet is a Gaussian, and this is the Gaussian, and you can clearly see that uh, this is a very useful filtering method for the narrowband filtering because Morlet Wavelet shapes, frequency domain shape is useful for the narrowband filtering. And okay, now I know my wavelet is working correctly. Now what I'm going to do is I'm going to use convolution theorem to filter out these noisy signal. So convolution time. Now, okay. Now first I need to length of my signal, and I have already calculated the length of my signal, but I am doing this again. We're going to have my signals length. Then I need a time vector. It is from 0 to n minus 1 divided by s rate. Okay. Now for the convolution theorem, this is the equation of convolution theorem. We need to first specify the length of convolution, and equation of this is this convolution length is equal to n plus length of wave time minus 1. This is the equation of the convolution length. It's basically this 2k minus 1. And after that I need to calculate the half width, and it is this I'm going to use flow function, and after that length function. So I will going to divide, okay, it should be this length, and I will going to add plus 1. Then this convolution will be going to in frequency domain, because frequency domain convolution is super fast. So I need to take the Fourier transform of my Morlet Wavelet. So what I'm going to do is I will going to take frequency domain response of my signal, and I will just going to use fast forward transform, and I will just going to specify Morlet Wavelet, and for the transform length will be equal to convolution length. So convolution length. Okay. Now I need to normalize this because the gain is enormous in these convolutions. So I need to normalize it. So what I'm going to do is simple. I will just going to normalize it by dividing it with its maximum value divided by absolute of maximum value of, and now I have normalized my signal. This is the normalized signal, and now I can do convolution. So I'm going to multiply my frequency domain Morlet Wavelet with a frequency domain of my signal. So what I'm going to do is I'm going to create a convoluted signal parameter, and after that I will going to multiply my frequency domain Morlet Wavelet with frequency domain signal. I need to take transpose of it, and its length will again we're going to equal to convolution length. But this is not over. I will going to take inverse transform of it because I need to inverse Fourier transform of this to again see this signal in the time domain, so I can compare it with my bandpass filter. And lastly, we will just going to take real part of this signal. Come signal from the half width point to and width point +1. Now the convolution is complete. What I'm going to do right now is I will going to plot this signal. Now let's do this and let's plot this signal. Let's plot it. Convoluted signal, and its title will be signal with Morlet Wavelet. Okay, fingers are crossed, and let's see. And this is the convoluted signal with Morlet Wavelet, and you can see it's very similar to our bandpass filter, but there are some differences. So let's see what are those differences are. So let's compare them with each other. So what I'm going to do is I will going to plot them together. I'm going to plot them and show it a signal and convoluted signal, and let's add a legend. First one is filtered, and second one is convoluted. Let's do this, and as you can see, they are almost same, but there are a few differences. First one is the gain is different. Combinator signals gain is lower than the filtered one, and this is the result of differences between frequency domain response. So what I'm going to do is I will going to compare the frequency domain response with each other. Let's do this. So I'm going to divide that figure 2. So what I'm going to do is basically this. Okay, I will going to press this, and I will just going to set limitation. It will be from 0 to 30. Okay, now what, let's plot frequency domain response of our Morlet Wavelet. So it is in here. Let's plot this, and enter, and I will going to add a set in here again. And now let's evaluate this, and you can see this is the frequency domain response of bandpass filter and Morlet Wavelet. And as you can see, bandpass filter frequency domain response is more like a plateau, but Morlet Wavelet is a Gaussian. So bandpass filters can contains much more energy, can contain signals energy much more than the Morlet Wavelet, and this is why the gain differences is happening. Now you can apply some normalized method to you can apply some normalizing methods to increase the gain of your conversion, but I am not going to do that in this video. So this is it. Thank you for listening to me, and see you next time.